Right. Hi, everyone. Let's talk about the complex logarithm. First, let's talk about logarithms over the reals. So recall that log of x for x positive is defined as the inverse of the exponential. What does that mean? So log of x is equal to y if and only if x is equal e to the y. Okay, so that was the situation for x in the reals. And so in complex, it would be the same definition. So it will be the same because we wanted to agree with the one on the reals. But it's also miraculous that it works the same way. Okay, so the complex function log z from the complex into the complex is defined as the inverse of the complex exponential. So same way, log z is defined as w if and only if z is equal to e to the w. Okay, so this is our definition of a complex logarithm. So let's do some examples. Want to find log of z for z equal to 1 over square root 2 plus I 1 over square root 2. Okay. So we observe that z is equal to cosine of pi over 4 plus I sine pi over 4. And so it's equal to e to the I pi over 4. Okay, so we go back to our definition. Let w equal I pi over 4. Then log of z is equal to log of e to the I w. W, which is equal to w I pi over 4. Okay, so that's a simple example. But here's something interesting. We could have done the following. Z, same z as above, is equal to cosine pi over 4 plus 2 pi, right? There's no difference when you shift things by a full angle, right? But that gives a problem. Implies the following. So this guy is now equal to e to the I pi over 4 plus 2 pi. So for w equal to I pi over 4 plus 2 pi, we get log of z, log of w, I pi over 4 plus 2 pi. And I think it's clear that we have that this is equal to e to the pi over 4. So we showed that log of z is equal to I pi over 4, but also log of z is equal to I pi over 4 plus I 2 pi. And you could have continued that. So in general, since z is equal to cosine pi over 4 plus 2 pi n, we get log of z is equal to I pi over 4 plus I 2 pi n. So hopefully something must look wrong to you. In the reals, a function sends one input to one output. But here, the same input z equal to I pi over 4 gets sent to multiple outputs. Okay, so we have the following situation. Log of z is equal to all of them. So I pi over 4, I pi over 4 plus I 2 pi, and so on. Where n can be 0, but also plus minus 1, plus minus 2, and so on. This is called a multi-valued function. And this is very common in complex numbers. Okay, so one input gets sent to many outputs. And we will mention how to get around this problem. But first, I want to do a few examples. So let me do one small example. Actually, I think we did. No. Let me give you the general fact. So a proposition, and then we'll do a lot of examples. All right, so let me summarize all what we wrote into one statement. Log of z has a real and imaginary part. I'm following the proof in the book, and is defined as follows. Is defined as log of absolute value of z plus I argument of z plus 2 pi n. So let's prove this. This is in your textbook as well. Right. So want to find u and v such that log of z is equal to uiv. So we want to find these two guys. Okay. Fine. We have z is equal to x iy. Okay. And right, so we have this. So using a definition of log, we have the following. We have x plus iy is equal e to the log z, which is equal to e to the u plus iv. Okay. Hopefully that's clear. This will give us a system of equations. What do I mean? So let's further simplify. We have x plus iy is equal to e to the u. And then by Euler's formula, cosine v plus I sine v. As we did in previous class, equate real and imaginary part. So x is e to the u cosine of v, and y is equal exponential times sine of v. Okay. Okay, let me repeat what we're doing. We want to find, the real and imaginary parts of log z. All right. So we will here we will solve for u and v. All right. Okay, let's do it. Okay, step one. We know that we have the following identity. So recall the modulus of z is equal to the square of the real part. Let me write it. So real squared plus imaginary squared, which is equal to x squared plus y squared. And so we use our system star. So we have EU cosine of u squared plus EU, v, sine v squared. Okay, factor out the exponential. and then observe that we get a summation of cosine and sine with the same angle, so we get 1. Okay, so we're almost there. Now we can find u. So we have that we have e to the 2u is equal to z squared. So these are just real numbers. We can take square root, and then we can take real log, and we got our real part. Okay, we found u. Okay. Find the imaginary part. Let's find v, which is the imaginary part of log. Here we found the real part. So real part of log of z is equal to log of the modulus of z. Okay. All right, so let's recall our system here. So this is our system. And we will take the ratio in order to cancel out the exponentials. Observe that y over x is equal e to the u sine v, e to the u cosine v. So we get the tangent of v. So v is the arctan of y over x, which from previous class, this is just the argument of z. So just to remind you, we have z is equal to modulus of z times e to the I. So recall, z has the following formula. It's equal to its radius times its phase. Okay. But again, right? Z does not have a unique argument. So recall, Z does not have a unique, how do you say, unique argument. Because z e to the argument z, you can always multiply by 1, which is e to the I 2 pi. Remember, 1 is equal to e to the I 2 pi. And so the argument changes. Okay. So yeah, let's finish it. We just showed that log of z has the following 2 parts. The real part, log of the modulus, plus I argument of z plus I 2 pi n. Okay, so from now on, you can use this formula Let me give a short summary of the proof. So we want to find the real and imaginary parts of log. And we start with obtaining a system and solving for u and v. First, we solve for u. And we find it to be, so we found it that u is equal to log of the modulus. Okay. Then we want to find v using our system, from our system. We find that y over x is equal to the tangent of v. Then we take inverse with arctan. And we found our v. All right. So let's do plenty of examples now for the remaining time. So this is example 2. So what was it? Yes. So want to find log of z for z equal to 1 plus I. Okay. All right. Yeah, we will use our formula from above. Okay. So first we observe that you can write z as follows. Actually, yeah, so there's two ways to do this. Let me see what the goal is. So the goal is write z in the form of modulus of z times e to the argument of z. Because then log of z is equal to log of the modulus plus I argument of z plus I 2 pi n, where n is any integer. Okay, so let's achieve our goal. So let me do it the slow way. So you can find that the modulus of z is the following. You can get that this is equal to what? Real part, so 1 squared, plus imaginary part, 1 squared, so square root 2. Okay. And now we want to find the argument. So argument of z is equal to arctan of imaginary over real. So arctan of 1 over 1, which is pi over 4. So z is equal to square root 2, 1 over square root 2, 1 over square root 2, ai pi over 4. So there's two ways. Either you find modulus and phase, or you try to do some trick where you multiply and cancel. and divide. Either way is fine, as long as you get z into the polar form. All right. So the punchline is that log of z is equal to log modulus plus I argument so log of square root 2 plus I of pi over 4 plus I 2 pi. Okay. So good. Now let me tell you a little bit about the picture we talked about that I showed you in the beginning. What's the meaning of this? So let me try to. So that image is the picture of log. All we're trying to say is, if you start with the point 1 plus I, so we're working with the same example. We're saying that the image is the following. So let me make it a bit bigger. So we have, how do you say it? So log square root 2, and this is pi over 4. So this here is log of z for n equal to 0, right? But then we have another guy, pi over 4 plus 2 pi, same modulus. So this is log z for n equal to 1. And you can keep going. So all that picture says is you have multiple images. So you have one image where n is, let's say, 0. Then you have another image where you shift it by 2 pi. Let me make it bigger, give you more space. So we have n equals 0, n equal 1, n equal 2. And we shifted here by 2 times 2 pi, 2 pi, no shift, and then negative shift. And so on. And a single point, pi over 4, has multiple images. So this is an image, this is an image, this. So you don't have to know this, but I just wanted to give you this picture that you might see if you Google complex logarithm. Please feel free to ask questions, but you won't be tested on this. This is only, so you won't be tested on this. Because it's quite complicated on this picture. Okay, but now let me talk a little bit. But we still want a single valued function sometimes. So we have the following definition. Is called the principal logarithm. Principal. logarithm. So it's the following. Denote log. So here we use capital L. Denote the principal logarithm as same thing, log of modulus. But argument of z is within minus pi to pi, i.e. N is equal to 0. So the principal logarithm in this picture is this guy. So we ignore all the phase shifts, and we only keep the 0 shift, so no shift at all. Okay, so let me do some examples, and then that will be the end for today. Example 3. All right. Yeah, let me start a little bit easy. So I want to find log of minus c, where c is just a positive number. Okay. So let's start a little bit slow. So we want to find this guy. Observe that minus c what is equal to c times minus 1. So let me write like this. Minus 1. And minus 1 has the following polar form, e to the I pi. Okay. So the goal is always to bring the input into a polar form, and we did it. So let me do both big and the small. So log of minus c will equal log of modulus of c plus I pi plus I 2 pi n. And the principal guy will just be the same. So log of c plus I pi, right? So there's no n. Okay. Yeah, let me do one more. Let's return to example 1. Want to find principal log of what is it? 1 plus I. Okay. We already found the polar form. 1 plus I is square root 2 e to the I pi over 4. So log of 1 plus I, principal log, will be log of square root 2 plus I pi over 4. Right? So we don't add any shift. This is indeed within minus pi. So no shift at all. Okay. All right. So that's it for complex log. smiley face, and that's it.